A very good morning. So in the previous class, we discussed about a transmittivity of the cover system. That is what? Tau is equal to tau r and tau a, and we derived tau r value as well as tau a value, and finally we got the tau value, and based on that also we solved a problem. Okay. So similarly, today we are going to discuss the transmittivity and observativity product, means tau into alpha. Okay. So transmittivity means so this is what the transmittivity. Okay. So means it's a tau value. Okay. And observative means it's a alpha value. So product of a tau and alpha, it's very important for the energy balance equation. We already know that in our previous class we discussed about that energy balance equation, and in that entire equation is multiplied by this transmittivity as well as observativity, tau and alpha. Okay. So this transmittivity, it is always based on a cover system. Okay. So if there is a cover system, means there is a glass. Okay. So generally we are using a glass. So that glass is that transmittivity, means how it will transmit the radiation. So if the radiations is generally either the radiations is a beam radiations or radiations from the diffuse radiations, whatever it may be. Okay. So that radiation is from the sun. Okay. It is directly falling onto the cover system, and this cover system generally made by a glass material or any transparent material. Okay. So through that it will transmit, and there is an interface, and that interface any radiations, if any radiations fall on that, it will start, okay, striking on the cover system, and one thing it will reflect and another thing refract. Okay. So refract means it will transmit through the media or a system, and reflect means it is just a reflect to the means it may be reflect back to the space, or it may be reflect and it may strike to the another surface. Okay. And the same thing is here also, same thing happens. The first, okay, if the radiations from the sun is directly falling onto the cover, and because of that transmittivity, okay, because of transmittivity it forms the tau value. First it forms the tau value. Okay. Then, okay, then there is an observer plate, means first there is a glass, okay, then observer plate. Observer plate is made by any metal, either maybe copper or aluminum, and it is coated with an black color just to observe the maximum radiations. And here also same thing, first it is from the cover, the radiations it will reaches the observer plate as an value of tau. Okay. Next, in the observer plate, again the observer plate should have an observability, means how much that heat will trap. That is what the product of transmittivity tau, and the capacity of observing, the capacity of that plate is called alpha. Okay. That is the first thing. So tau into alpha, first it will enter. Okay. Next, so here also same thing, it will strike the observer plate, tau into alpha, it is observed in the observer plate, and some amount, and in the some amount of the again radiations will reflect, same like a previous one. Okay. And again it will reflect, and again it strikes the cover, and again it will reflect. Okay. Reflect, then again it strikes the observer, then there is a reflection, then refraction. The same thing will continues. Okay. So that this transmittivity and observativity product can be defined as, okay. So just a minute. Yes, it is the ratio of the flux absorbed in the observer plate. the flux means amount of the radiation is absorbed in the observer plate. So here the amount of the radiation or radiation flux is absorbed in the observer plate into the a flux incident on the cover, means how much the flux is incident, means this is a cover, so how much flux is incident on this cover and how much the flux is absorbed in the observer plate. The ratio between these two, is called as a transmittivity observative product. Means here if 100% radiations is fall on the 100% radiation is fall on this cover system, means only 60 to 70% will enter and only 50% will absorb. Okay, so finally we get only 50%, and rest of the 50% is waste due to because of the reflection, re-reflection, re-radiation. Like this it will waste. Okay, and this is denoted by tau into alpha. This can be denoted by, this entire thing is denoted by tau into alpha. Okay, and appropriate subscript of B or D. We can go with B or D, means either beam radiation or a diffuse radiation. This entire thing is with a B or D, means a beam radiation or an diffused radiation. And an expression of this transmittivity product will be means in this we are going to discuss on this equation, the equation for this observative and transmittivity product. So out of the fraction, I told the tau, okay, the tau transmit through the cover system. First the radiation will transmit through that cover system and it is become an tau. A part of this absorbed, okay, and a part of is diffused, means some part of is absorbed directly and some part will again diffused, that is what reflect. Okay, and out of the reflected part, again in this reflected part, so the tau value, some part is absorbed with the help of this observer plate and it's become an tau alpha. Okay, and some part of this tau will reflect or will diffuse, it is also called as diffused, and it is become the tau 1 minus alpha rho s, or it is rho d, we can call it as. Clear? We can call it as a rho d. And reflected part of this portion is again transmitted through the cover system. Again it will transmitted through the cover system and a portion of reflected back into the observer plate. Means again this some portion will reflect and strike on the cover system. Okay, and in this cover system some part of this will reflect back into the space directly, waste, and some part will refract and again it will to the observer plate. Clear? And again in this some portion again will reflect and some portion will absorb and some portion will reflect, and this is strikes the cover, and here when striking some portion will reflect and some portion will refract. Again that refracted onto the observer plate, it will absorb some portion, and here on that some portion again there is an reflect. Clear? And again this reflect striking on this cover, some portion will refract and some portion will reflect. These reflected are wastage, means directly loss of the radiations. Okay, and refracted will again onto the observer plate and it will absorb, and this is will continuous. It is a continuous one. So in this way radiations will first transmit, then absorb, then reflect, then transmit, then absorb, then reflect. Like this it is a continuous one. Okay, and this process of this absorption and reflection is at an observer plate surface goes on, and it is infinite one, and it is indefinitely, means continuous. We don't know the definite process, it is a continuous one. And for the quantity of involving such a successive small quantities, we are going to consider for our equation. Finally we can write the net a fraction absorbed, means in the previous. So this is what the net, absorbed the heat energy or radiation flux is observed with the help of this observer plate is this one, tau alpha 1 plus 1 minus alpha rho d, and tau alpha 1 minus alpha whole square rho d whole square. Like this it will keep on going, and we can write it as, this is the equation, we can write it. Okay, so this is a, we can take this tau alpha as a common value, and this is for first, it is an we can take 1. Okay, next 1 minus alpha rho d, then plus 1 alpha whole square rho d whole square, like this 1 minus alpha, okay, so whole cube rho d, like this it will goes on. And finally we can take that equation as the fraction of this observer plate, it is tau alpha divided by 1 minus, okay, 1 minus alpha rho d. So this equation you should remember. This is the product of transmittivity and observativity. And in the symbol rho d, it represents, in the symbol there is a rho d is there. This symbol represents a diffused reflective of the cover system, a diffuse reflectivity of the cover system. Okay, and it can be found by determining the value of, it can be determined by determining the value of this one. So tau a, okay, tau a 1 minus tau r. Okay, we already derived what is meant by tau a and tau r in the previous class. And for the cover system, and incident angle is 60 degree, for the incident angle is 60 degree. And in that rho d value is 0.21 for the 2 glass cover system, if you use 2 glass cover system. Okay, and for 1 glass cover system this value is become 1.15. If it is 2 cover system, if you go with the 2 cover, it is 0.21, means in the problem they given 2 cover, 3 cover or 1 cover. If the cover is 1, we can take the value of 0.15. If the value, if the cover system is 2, we can directly take rho d value as a 0.21 for the calculation purpose. Okay, so next is overall loss coefficient and heat transfer correlations. So here the next important equations you have to remember is this one. It is an overall loss coefficient. So far what we discussed is observativity, transmittivity we discussed, and it will observe the radiations. But next equation what we have to discuss is the value of Q, means in the energy balance equation. We already know that in the energy balance equation, so that energy balance equation Qu is equal to AP S minus Q1. So this for AP and S we already discussed, observer plate area, and S is the radiations incident on that cover system. Okay, and Q1 is the heat loss. Okay, that Q1 value we are going to discuss. Okay, so that Q1 is the total overall heat loss, overall heat loss of the liquid flat plate collector. And that overall liquid flat plate collector, it having some components like, so Q1, this Q1 is given by UL. So UL AP TPM minus TPA, where UL is the overall loss coefficient. It is the overall loss coefficient. Clear? There are 3 types of losses. One is the top loss, bottom loss, okay, and side loss. So this U indicates that UL indicates that it is an overall all these 3, okay, all these 3 losses that we will discuss in the later. Okay, and so UL is the overall loss coefficient, and AP is the area of the observer plate. So there is an observer plate, okay, liquid flat plate collector is having an observer plate. So that area, okay, length into width, that is the area of the observer plate. And TPM, it is the average temperature of observer plate. So average temperature of this observer plate, and TA is the average temperature of observer plate. Okay, So here, average temperature of atmosphere, okay, or ambient temperature. It's an ambient temperature, okay, or surrounding air temperature. You can call it as a surrounding air temperature. So Ta is the temperature of air, okay, and TPM is the temperature, average temperature of observer plate. Clear? Okay. So this is the equation we are going to consider for overall heat loss. For overall heat loss means you should remember Q1, QL, okay. So either you can call it as a QL or Q1, okay. So you can take this as an QL, small l, okay. Overall heat loss is equal to U, capital UL AP into TPM minus TPA. So UL means overall loss coefficients. AP is the observer area, we already knew that in the energy balance equation, and TPM is the average temperature of observer plate, and TA is the ambient temperature or atmospheric air temperature. Atmospheric air temperature. Okay. Next, the heat loss. So next is the heat loss from the collector. It is the heat loss from the collector. Means that is what the we have to find out that U equation. Okay, if you want to find out the E equation, so we know that heat loss, that Q1, just only we know that Q1 equation. So the Q1, just we written this QL, okay, is equal to UL AP, okay, T PM minus TA. So this is the equation. It's a overall heat loss, and this overall heat loss we can also write like this Q L is equal to QT, QB and QS. We can write this equation as QL is equal to QT, QP, QS. So QL means overall heat loss. So it's a overall heat loss, and QT means a rate at which heat loss from the top, means in the observer plate is there. Okay. So this is a observer plate and liquid flat plate collector, okay, and this is a cover system, okay, and observer plate, and it is insulated with insulators, okay, everything is there. That entirely it called as a liquid flat plate collector, and this is having some multi layers. This is here this is an insulators, and here there is a observer plate and cover. So here there is a top loss is there, top heat loss, okay, and bottom heat loss and side heat loss. That is what we can written as a rate at which heat loss from the top, a rate at which heat loss from the bottom, and the rate at which heat loss from the side. So this collectively we can write it as a total heat loss of that liquid flat plate collector, and this can be written as QL is equal to QT plus QB plus QS. This is also equation, and the same for this QL we can also write it as a Q UL AP TPM minus TPA. This is also equation we consider for both the conditions, total heat loss. Clear? And for individual, okay, so QL we already know this value, and if you want to heat loss in the top, okay, this is the equation, bottom this is the equation, and for the side this is the equation we are going to write. So instead of QL we are this QL is for overall, okay. If you want to consider only for the top, so QT which is equal to UT AP is same, TPM is same, and TA is same, but only thing is UT will changes, and for the bottom this UB, and for the side it become US. Clear? So this is what the heat loss coefficient. So heat loss coefficient in the top, heat loss coefficient in the bottom, heat loss coefficient in the side. Clear? And if you want to consider for whole, this will become a QL and this is UL. Okay, so this equation. So UL is the total overall heat loss, but UT means only for coefficient for top, coefficient for bottom, coefficient for side. Is it clear? And this it is based this AP, we already know that it is an observer plate, and the temperature difference, always there is a temperature difference between the TPM minus TPA. So TPM is a higher temperature, means inside the observer plate it should be higher temperature, and outside surrounding temperature should be lower one. There is a temperature difference. And the loss can be also pictured in the term of a thermal resistance, okay, and which is shown in this. And the overall loss coefficient of the an important parameter, since this measured in the all the losses Q, top, bottom as well as side, and this value we can ranges 2 to 10 watt per meter square Kelvin. Okay. Yes, this is a U. From that we can take as UL is equal to, okay, UL is equal to UT plus UB plus US, and this is a, okay, yes, this is a TA means the ambient temperature, and this will that is what UT QT, and this is a UTM QB and TA, and equivalent. So this is equivalent to, we can write it as QT QA, sorry, TA QL, which is TPM. Finally, if you want to attain this TPM, okay, so that equal to TPM, the total temperature, which is equal to TA into QL. QL is the overall heat loss. So this equation you should remember. Okay, so you have to remember this U equation as well as you have to remember this Q equation, but primarily you should remember this QL is equal to UL AP TPM minus TA. These equations you should remember for calculation purpose. Okay, so now come to the first you have to find out the one by one you have to find out, means the heat coefficient. So that value, that is what, UT top, UB bottom, US side. So that these values you should know, means the equation for these values. So the first is the top loss coefficient. First thing is the top loss coefficient. So the top loss coefficient UT. So the top loss coefficient we can write it as UT, we can write it as this is, okay. It is evaluated by considering. So here what happens in the top loss, by considering convection and re-radiations. So here the loss will take place either in the form of convection, and re-radiations, means once the radiations is fall on the cover, then it will divided, means it will polarized into refraction and reflection. So reflection is the waste, okay, it is reflect to the space, it is a wastage, that is what the loss. Okay, that is what a re-radiation, we can call it as a re-radiation. And convection, so next is the loss is convection. These two are common in the top loss. The top loss coefficient is with the convection as well as re-radiation losses from the observer plate towards the upward direction. Yes, you just observe in this is the observer plate, and here there is a reflection, okay, it is always towards the upward. So if the any radiations towards the upward direction, means it is just simply an wastage, okay. So that is what here reflection. So this reflection is wastage, and here again once it is refract, okay, means passes through, again there is an interface, again there is an a reflection. So some portion will again reflect back and it will move to the space, and these are all a common convection as well as re-radiation losses in the observer plate, and it all shows that upward direction. So any upward direction radiations is simply a loss in the top cover, that we can consider as a top loss coefficient. And for this purpose calculation, we can assume that this transparent cover, we already know that it is an transparent cover, and the observer plate constitutes a system with an infinite layers. Means it is an infinite layers of parallel surfaces, and that flows the heat from one dimension, and we can consider this is a one dimensional heat flow, and the heat flow is always steady state heat flow, and it is one dimensional. And it is further assumed to be a temperature drop across the thickness of this cover is negligible. Okay, that is most important. We can neglect the temperature drop across the thickness of the cover. If the cover thickness is more, if the cover thickness is less, whatever it may be, the temperature across the thickness we can neglect it, means it is very small one. And for this interaction between the incoming radiation and observed in the covers, and the outgoing loss may be neglected. Okay, and outgoing re-radiations is a large wavelength. So some portion we already know that some portion will back to the space, that is we can call it as a re-radiation. And for these wavelengths the transparent cover will be assumed to be an opaque, then it is very good assumptions, and this material is glass. If we consider glass, we can assume all these conditions. And this diagram you can just observe. This is what the diagram, this is the sky, means after reflection that radiations will reach the sky. Okay, and here in that steady state the heat transferred by the convection and radiations between some stages, means first stage is the observer plate and the first cover. If you use cover 1, cover 2 and observer plate, okay, there are so many covers. Then the first thing is observer plate and the first cover, observer plate and the first cover, first thing. Second, the first cover and the second cover, the first cover and the second cover. So this is the second cover, and this is the first cover, and this is the observer plate. Okay, so there is an interaction between observer plate and the first cover and the second cover, and the second cover and the surrounding, Okay, so these things we have to consider. Okay, so there are parallel surfaces, these are all parallel surfaces. So here this is the observer plate, and this is the cover 1 and cover 2 and the surrounding. So there is an interaction, first interaction observer plate and the first cover, second interaction observer plate first cover first and cover second, and third is cover second and the atmosphere. Like this, step by step there is an interaction. Okay, and hence we can consider, by considering all these, and we can get the equation. Okay, so that is QT divided by AP, QT divided by AP. Okay, so heat loss in the top, QT means top heat loss, divided by AP. So AP is the observer plate, which is equal to HP, okay, minus CL into TPM minus TPCL, and alpha observability into temperature TPM, observer plate temperature to the power of 4 minus CL, means cover 1 temperature to the power of 4 divided by 1, okay, epsilon P plus 1 by epsilon C minus 1. Okay, so by reducing this equation we can write it as, finally we can write this equation as HW into TC2 minus TA plus omega, means that is what, alpha or omega into epsilon C T C2 to the power of 4 minus T sky to the power of 4, means HW means convective heat transfer coefficient in the topmost cover with the surrounding, means here topmost cover with surrounding. Next, HP minus C1 means convective heat transfer between observer plate and the first cover, and C1 minus C2 means cover 1 and the cover 2. So this is the interaction, convective heat transfer, okay, heat transfer. And TC means temperature of the cover 1 and the cover 2, and T sky means temperature of the sky or atmospheric temperature. Epsilon P means emissivity of the observer plate, C means emissivity of the cover. Okay, so this equation you should remember. And next, the heat transfer coefficient between, so that previous one what we consider is for the parallel surface. If the inclined surface, If it is an inclined parallel surface, then we can consider these equations. NUL means we have that NU means it's a Nusselt and RA means Rayleigh's numbers. If it is an inclined means we go with Nusselt's and Rayleigh equations. Okay, these are the some standard equations you should know. Okay, so if it is inclined parallel surface, if it is a normal straight parallel surface, the previous equation we consider, but if it is a inclined and parallel, then we have to go with these equations. Nu, okay, 1, if it is Rayleigh's equations is more than 1708. If NUL, which is equal to 1 plus 1 plus 4, 4, 6, this equation, if it is between the Rayleigh's number is between 1708 to 5900. If it is more than 5000, okay, then we have to go with this up to 9.23 10 raised to 4. If it is more than 9.23 10 raised to 4 up to 10 raised to 6, we can consider this equation. So it is just because of the Rayleigh's numbers. Okay, based on Rayleigh's number, we can consider the Nusselt's equation. And the final is heat transfer coefficient at the top cover. So final heat transfer of the top cover HW. So in the previous equation there is HW is there. That HW given by a simple equation. Okay, it's a convective heat transfer coefficient HW. Convective heat transfer coefficient HW at the top cover. It is referred by the equation HW is equal to 5.7. Okay, into plus 3.8 V infinity. Okay, so in the sum equations HW is equal to 8.55 plus 2.56 V infinity is also taken, and in this equation HW is watt per meter square Kelvin and V infinity is an wind speed. It's an wind speed. Wind speed is also contribute for that equation. Yes, and the last in that equation T sky. So T sky in the equation is there, and that T sky equation is given by T sky is equal to TA minus 6. It is a standard equation. T sky, the temperature of sky, which is equal to temperature of atmosphere minus 6. Whatever the temperature of atmospheric, minus 6 degree, which gives the T sky temperature. Yes, finally what we want is, so we want this UT means the top coefficient, top loss coefficient. That is what we needed, and this we can written as by using all the equations. Okay, this UT finally what we want, because UL is equal to UT plus UB plus US. That is the top, bottom, side. For this top, okay, we need all those components what we discussed so far. Okay, so finally the empirical equation representation. Finally, you just remember this equation. UT means the top loss coefficient, which is equal to M. Okay, so M divided by C divided by TPM into TPM minus TA. Okay, divided by M plus F raised to 0.33 plus 1 divided by HW. Okay, that is what root. So root of all this, or else you can write it as minus 1 raised to minus 1, or root we can consider, plus this term plus. Okay, and here there is an omega. Okay, and into T PM square plus TA square TPM plus TA whole divided by EP means emissivity. That is what. Okay, so previous we discussed, that is what the rho epsilon P means emissivity of the observer plate, and epsilon C means emissivity of the cover. Clear? And M, so in the equation M represents, that is what the number of glass covers, if it is a 2, if it is a 1. Clear? And C represents, okay, that C, it is an equation for that C 365.9 into here that we consider a beta value, and f it is equal to 1 plus 0.04 HW, 0.005 HW square, 1 plus 0.091 m. So this equation you should remember. There is no derivation for this equation. You simply remember this equation, and it helps for calculation purpose. Okay, this is what a top loss coefficient equation. And next is bottom loss coefficient. Similarly, what we discussed is top. Similarly, the bottom loss coefficient, and this bottom loss coefficient is with respect to always, it is with respect to always considering a conduction. There is a conduction and the convection. There is no re-radiation. Here there is no re-radiation, only a conduction, only the conduction. Okay, so this is a bottom. So here in the bottom either maybe conduction or maybe convection will takes place, and it represents downward direction, means from the observer plate, if any heat flowing from downward, that represents to the bottom loss coefficient. If any represents to upward, that top loss coefficient. So upward indicates that top loss, and bottom downward indicates that bottom. If it is side, indicates that side loss. Okay, so here either it may be conduction, okay, or convection. There is no re-radiations, and it will be assumed that the flow is one dimensional. Here also same thing, we consider it is a one dimensional flow and steady state. In most of the cases, the thickness of the insulation, means we are using insulation at the bottom, the thickness of the insulation provided in such that the thermal resistance associated with that conduction, okay, it will dominates, means there is no convection, only the conduction will dominates because of the insulation. If you go with maximum insulation, the loss will can reduced, and neglect the convection resistance. Only if you want, only you can consider conduction, because go with the thickness of the insulation. The more the thickness, more will be the conduction. And here this given by the equation UB, which is equal to Ki divided by dou B. Ki means thermal conductivity of the insulation and thickness of the insulation. So if you want to here this coefficient is increases when thickness of insulation increases. Okay, if you increase the more thickness, okay, that increase the top loss coefficient. Okay, the thermal conductivity of the insulation. So if you want to reduce this component, means we can go with less thermally conductive material, so that it will decrease, or you go with a less thickness of the insulation. And come to the last one, the side coefficient. Okay, so side coefficient always represents in the bottom with a side. Okay, it will assume that the resistance is dominates. Here also it's a one dimensional and steady state, and it the flow with represents in the side. You just observe in this figure, this represents the side heat loss. Qs is the side heat loss, Qb is the bottom heat loss. Okay, so this Qs we can written as 2L3 into L1 plus L2 Ki TPM minus TA divided by 2 rho S. Rho S is the thickness of the that side thickness, side insulation thickness. And finally we can write this as US. US is the coefficient, side coefficient is equal to L1 plus L2 into L3 Ki divided by 2 L1 L2 rho S. So rho S is the side insulation thickness, Ki is the thermal conductivity of that side wall. Okay, and by US and UB, and we already got the UT top. So finally by all these, okay, so UB and US, finally it will give UL. So UL is the total overall heat loss coefficient, which includes top, bottom as well as side. And for the side this is the equation, and for the bottom this is the equation, and for the top previous slide we have that equation. Okay. Yes, take this problem. Calculate the overall loss coefficient. Overall loss means UL. UL is equal to UT, US, UB. For the flat plate collector with a 2 glass, M is equal to 2. Okay, they given M is equal to 2. With the following data, these are the following data. The first is observer plate L1, L2. That is the dimension. That is the dimension of the observer plate L1, L2, which is needed for our calculation purpose. Spacing between the plate, first class and second class, cover L. It is 4 centimeter. Spacing between second and first class, it is 4 centimeter. Plate transmittivity, that is what rho P and rho C, they given 0.9 to 0.88. And collector tilt, that is beta, is also given. And minimum plate temperature TPM, they are given 70. Ambient temperature, air temperature is 24. Wind speed is also given, V infinity. And the black insulation, that is what rho dou B 8 centimeter. And that is what we needed in the UB and US. These two we needed. That is side insulation thickness, bottom back insulation thickness, 8 centimeter, 4 centimeter, and thermal conductivity, that is Ki, that is 0.05. So these are the data given in the problem. Based on these data, you have to find out UL is equal to UT into UB into US. Yes, one by one we are going to discuss. First, we have to find out the T sky temperature. We already know that T sky is equal to TA minus 6. TA means it's a ambient temperature or atmospheric temperature they given, minus 6, that gives the this value. That is what? Okay, so we got that T sky value is, this is the T sky value. Next is we need value of equation, that is what? THW. Okay, we need a HW value. So HW, we already equation. From that equation, we need a V infinity, that is a wind speed. It is given in the problem. By substituting, we got that HW. So once we got these values, okay, directly go with the top coefficient, that is what? UT. And for the UT, we need a values like C, we need a value, F, we need a value. Okay, so for the F, HW already we got the value, TA is given, okay, M is a number of covers is also given, and substituting all this, we got the value of F. And C also we have that equation, and for that we need a beta. So beta, they given 20 degree in the problem. If you substitute that, we will get beta value. Okay, and C and F, once we got that value, and directly we know that UT, this equation you should remember. Okay, and finally you substitute all the values. F we already got, M we know, TPM is given, TA is given, HW we just got, M is a number of covers, C also we got the values. And if you substitute all these values, okay, in this equation, finally that UT, which is equal to, and after simplification, finally we got the UT value is equal to 3.63 watt per meter square Kelvin. Similarly, we need a bottom. So bottom equation we have UB is equal to Ki by rho B. We have these two data in the given data, and substitute and find this. And second side we L1, L2 is given, okay, and these values are also given, and substitute and find out US. US is the, that is the a side coefficient, is the bottom coefficient, and previously top coefficient. And if you want overall coefficient, that is UL is equal to UT plus UB plus US. And if you substitute all those things, that will contribute for the overall heat loss. This is the final equation, 4.59 watt per meter square Kelvin. Okay, so this is how we have to find out the total overall heat loss coefficient by individually find out top, bottom as well as side. And all these equations we already have that equation. By substituting this equation with a given data, we will get the final answer. Okay, and this type of problems you will get in the examination. Okay, so in the next class we will continue.